Okay, our next speaker is Jeffrey Parker, and he's going to tell us about self-consistent modeling of multiscale turbulence and transport.
Okay, thanks for the introduction. And just to clarify, I'll be really talking about multiple timescale turbulence and transport. So my name is Jeff Parker. I'm a recent postdoc at Lawrence Livermore National Laboratory. And can you hear me? And these are my collaborators. So this will be a little different talk than most. I'm the only person, I believe, talking about fusion plasmas and turbulence. And so I won't get into the detailed physics. I'll just give you a brief background. And I'll spend most of my time talking about a numerical method for solving the kinds of turbulence and transport systems that we think arise in tokamak systems. But from what I'm hearing at this conference, this is a pretty generic kind of topic. So fusion reactors are an attempt to create clean electricity from fusion reactions with no greenhouse gas emissions, no radioactive waste. And the fusion reaction that we would probably use in the first generation of fusion reactors is the deuterium-tritium reaction. And it's called magnetic because we confine a hot plasma in this tokamak-shaped, or it's a torus-shaped device called a tokamak using magnetic fields. So these fusion plasmas are rotating. They support a panoply of waves. They're turbulent, they're hot, and very complex. And they have to be kept hot so that the plasma, the particles, can get close enough to overcome the Coulomb repulsion and fuse. And so the problem is keeping these plasmas hot, but turbulence is the primary source of heat loss. So we want to better understand the turbulence and predict it and ultimately control and reduce it. Just a brief mention of the ITER project, which is a multinational effort to demonstrate the feasibility of fusion power. It'll be the first reactor to get more fusion power out than you put in to run the machine. So gain of 10 for 500 megawatts. And this is a very large machine. There's a person right there at scale. And construction is currently underway in France. So I'll spend a brief moment talking about the gyrokinetic theory, which is the workhorse theory for understanding low-frequency fluctuations in magnetized plasma. And so first, I'll motivate why we need to use a kinetic description at all instead of a fluid description, so here's some kind of Fokker-Planck, Boltzmann type of equation. F is a phase-based distribution of particles, depends on both space and velocity. And if you look at the collision time resulting from two-particle binary collisions, this is much, much longer than the turbulence timescale of interest. So it's not collisional. A fluid description isn't really sufficient. So we're pretty stuck with the kinetic description. But the turbulence timescale is also much longer than the gyration timescale for a charged particle to gyrate about a magnetic field line. And because of that separation of timescales, you can average over that motion and not only go from 6D to 5D, but also eliminate that fast timescale. So this is called the gyrokinetic theory, where given that separation of timescale, you average over the gyro motion, and now you have a reduced description, which is three-dimensional in space, two-dimensional in velocity. And now you're looking at the dynamics of charged rings, sometimes called gyrocenters, instead of particles. So you get something that's called a gyrokinetic equation. It's, again, an equation for a distribution of gyrocenters in a reduced phase space. So gyrokinetics is widely used. And even Sheldon, from the Big Bang Theory, he's analyzing a particle motion in a magnetic field. So as theory and as computational power march on, the fusion community is moving towards comprehensive simulations of plasma turbulence, trying to get more and more realistic. So just to give you a typical example of what state-of-the-art simulations might look like, so some recent simulations that performed a global type of simulation for a tokamak. This was one in England. They were able to simulate almost the entire machine radially using about 10 billion grid points. And this is not to say that all the physics is understood or is incorporated into these simulations, but they're pretty good and they're always getting better. Now, of course, there are at least two goals from simulations. One is to understand the detailed dynamics and physics microscopically of what's going on. But a second goal, which is really the focus of this talk here, is more quantitative, to predict really the macroscopic profiles and the gross levels of overall turbulent flux. And this is actually given something like heating sources or particle sources, something physical. So most of the simulations these days, or almost all the simulations really, would specify the profiles like temperature or density from the experiments, measured from the experiments. They don't self-consistently predict those profiles. So that's the goal of what I'm trying to do, is to self-consistently calculate the profiles and the turbulence together. And it turns out that the turbulent fluxes in the core of the plasma are sufficiently small that there is a very long time scale between the turbulence time and the evolution of the macroscopic profile. The turbulence time is around 10 microseconds. The energy confinement time is something like a second. So if you're going to do direct numerical integration of turbulence up to the long time scales, that would be very, very computationally expensive. So the question is, assuming you have the separation of time scales, how can we efficiently study self-consistent evolution and get an accurate prediction of the profiles? And some approaches to this kind of multiscale modeling are called equation-free, where you don't necessarily know equations for the macroscopic variables. But here, I'm going to assume that you have derived explicit equations describing both the slow evolution and the fast evolution. Schematically, you've got slow equation, fast equation. And the method I'm going to talk about, and something that maybe is often the case, is that the slow equation is of lower dimensionality than the fast equation. So if you expect the mean variables to be axisymmetric or have some kind of symmetry, then this will be lower dimension. So getting back to gyrokinetics for a second, there's a theory called multiscale gyrokinetics, which is an ordering scheme in which you can derive closed equations for both turbulence and transport of this form directly from the 6D plasma Fokker-Planck kinetic system. And so there's some ordering scheme where it works out, and that's what we're going to be using. So there were a couple of, about 6 or 7 years ago, there were a couple of initial attempts to implement that multiscale gyrokinetics, and they used an approach with local turbulence models. So in contrast, I'll be talking about a global approach, but first just to describe what they did. So people here are probably pretty familiar with the local simulation approach, which is based on a spatial scale separation between equilibrium and fluctuations. You typically fix the value of the equilibrium and its gradient at some point, and that allows for very convenient boundary conditions, typically periodic. So in tokamaks, the local simulation is often called magnetic flux tube, and this has analogs in other contexts as well. The way that this approach would work, this coupling approach would work with local simulations, is you choose a few points, a few radii along your tokamak, say n, and you have n points on your radii, and at each point you do a local simulation, and you would calculate the turbulent flux resulting from that simulation, and then you use that flux to evolve the transport equation. And so you take these large jumps in time on the transport time scale, and you get some final solution. So these were done several years ago. They suggested informally that this maybe wasn't very promising for various reasons. So we are going to try a global approach, which is conceptually simpler since you only have one simulation. But it's more difficult in practice due to different numerical methods required, and you need more careful handling of boundary conditions. So because we're not going to use a local approach, and now we're not directly incorporating the spatial scale separation, the global approach can capture physics that would be missed entirely in the local approach. But we'll still be assuming the existence of the timescale separation. And the global approach may even be cheaper than this local approach. If you estimate the number of radial grid points needed just to get convergence, at least for our problem, some estimates suggest that you actually would need fewer total radial grid points. So that's the goal, is to do this kind of self-consistent calculation of macroscopic profiles and global gyrokinetic simulations. So we're collaborating with Frank Yanko and Daniel Told at UCLA, who have developed the GENE gyrokinetic code. And so now I'm going to step back from plasmas and fusion and gyrokinetics and just talk about generic transport models. So if the plasma talk was boring you can wake up, pay attention. So I'll use this as a generic nonlinear transport model where n is maybe density or temperature, gamma is your turbulent flux, S is your sources or other local terms. And all the details of the turbulence now are going to be hidden inside this gamma function. So just some gamma of n that you get from a turbulence code. For fusion plasmas, we consider the turbulence to be primarily diffusive, where the flux is proportional to the negative of the gradient. But this diffusion coefficient can depend strongly on that profile gradient. So you might have d, which is your gradient to some power p. And in reality, we think that it's temperature gradients driving the turbulence due to thermal gradient instabilities. And p might be 1 to 2, or maybe a little bit larger, not in our tokamak turbulence. So if you have this gradient-dependent diffusion coefficient, if you analyze some simple schemes for solving this nonlinear equation, it turns out that you get numerical instability if p is bigger than 1, which would constrain your time step to be extremely small even for semi-implicit integration. And because we want to take very large time steps, that motivates using a fully implicit time step of the transport equation. And so the question is, how do we solve this nonlinear equation that we get from a fully implicit time step? So really the method is going to be talked about the method that I'm going to present. And the fusion community has been aware of this kind of multiple timescale problem for a long time, but how to do this numerically is a problem which I don't think has really been addressed. So I'm pretty ignorant of the geophysics and astrophysics literature on this topic. And so one thing I'm curious is the kind of numerical methods that are used in other fields. So for example, Edgar was mentioning something similar. And I think, so he would have a d, which corresponds to his Nusselt number with his scaling going like a Rayleigh number to the 3/2, which corresponds to p equals 1/2. So the strategy I'm going to be talking about is the LoDestro method, which is it's a numerical method for solving this implicit time step equation. And so I'll list some of the key elements of that here with more detail on the next few slides. So one is the key is really to represent the turbulent flux as diffusive and possibly convective, and then use a Picard iteration to converge to the nonlinear solution. And so we're not using Newton steps, which means we don't take Jacobian, we don't need to calculate Jacobians or Jacobian vector products. We use an average over iterates to stabilize the iteration, which I'll talk about in more detail. This is a computationally advantageous scheme, at least in principle, where you can take a transport time step of this equation with a total cost that is comparable, or maybe just a few times, what it would normally take to run a single standalone turbulent simulation to steady state, to statistically steady state. This method works with either local or global simulations, and it is most efficient if your transport equation, if your mean variables are lower dimensionality, so that the implicit time step can be quickly done. So this is really the heart of the method. This is how it's going to work in practice. Here's the nonlinear equation, and for iteration, I'm going to introduce a subscript L to represent the Lth iterate. And here's the main step. You represent the turbulent flux of iterate L as a diffusion coefficient evaluated at the previous iterate and multiplied by gradient evaluated at the current iterate. This is a form of Picard iteration. And the way you get this diffusion coefficient is you evaluate the turbulent flux using the profile of the previous iterate, and then you divide by the gradient of the previous iterate. And just to note that the turbulent flux gamma, this is a choice of representation, and you don't have to represent it as purely diffusive. If you had a reason to, you might represent it with partially as convective flux and partially as diffusive flux, and the scheme would essentially work the same. But so let me just, for simplicity, assume it's going to be diffusive. And so if you plug that into your implicit time step, then you now have a tractable equation to solve for each iterate n. So this is now linear in the new iterate nml, and so you can solve this with the linear methods. And so if it converges, and this is bolded because it's a very important point, if it converges, then it doesn't matter how you represented it, because it's going to be the right answer. But of course, the representation will affect your convergence properties. And just to contrast this with Newton iteration, which is what some of the earlier attempts did, they would represent the flux as the flux at the previous iterate plus some Jacobian term. And so this requires calculation of the Jacobians, which are not only computationally expensive, since you have to run separate turbulent simulations, but since fluxes are intrinsically noisy, because there are statistical fluctuations in your simulations, unless you run for extremely long time and time average, these noise in the fluxes are going to be amplified when you calculate your Jacobian. So it's nice to avoid the Jacobian calculation. So let me return to our Picard iteration, and again consider a model diffusion coefficient where your d depends on the gradient to some power p. If p is greater than 1, it turns out that even this scheme is unstable. And there's a method to stabilize it by replacing d or gamma with a version where you average over iterates. So this is essentially equivalent, or the method that we're using is an exponentially weighted moving average, which is equivalent to relaxation. So if a here is less than 1, that will stabilize the scheme. But it really looks like p, if p equals 1, is a critical point where the extra nonlinearity of p greater than 1 makes this a much harder problem to converge. So just a couple other things. So I mentioned this split into diffusive and convective pieces. You can also do this if you expect that D might be negative somewhere. So if you have a non-local problem where the flux runs uphill, up a gradient, then this representation can ameliorate that problem. And then I want to just spend a few moments talking about why this is computationally advantageous and how we can take a transport time step with not much more than the time it takes to run a standalone turbulence simulation. So consider this loop where you've got a turbulence code running. You calculate some kind of flux. It's given to the transport equation. You take your iteration, and so now you have a new iterate n that you can return to the turbulence simulation. And then this turbulence simulation, you can run it for a little bit, but it doesn't necessarily have to be the entire time it would take to reach statistically steady state on its own. And then you can return that and repeat the cycle. So you can't see it here, but I drew this as a pretty small interval, these two lines, suggesting that you might only need to, when you're iterating this turbulence simulation with a new profile, you might have to integrate only even for just a few eddy times before doing this iteration. And that's because the Picard iteration is a pretty slow process. They're not changing much on each iteration. And so I'm going to suggest that if you do this iteration with only a few eddy times on the turbulence code, the total time it might take to do this transport step might just be a few t steady state. So this method was successfully tested for a simplified planar geometry, this 2D Hasegawa-Wakatani model. So what this diagram is showing is the long time steady state of the density, the final density minus the background density. So showing both the coupling method using the timescale separation compared to a direct simulation to the long timescales. And they're in excellent agreement. And the multiscale method was a much faster. And in this particular example, the method did handle regions of non-diffusive transport. There were also some promising first results using 2D transport coupling, where the equilibrium was 2D. And so in progress are coupling these transport equations and the 5D gyrokinetic simulations. So I don't have results on that yet, but it's in progress. The transport equation is, I'm going to be beginning in 1D, and then if you've got really fast rotation, you can get to 2D equilibria. But it makes it very simple that these tokamak equilibria are 1D. Okay, in conclusion, I've described the LoDestro method, which is a strategy for implicitly time-stepping a nonlinear transport problem in which the turbulent flux might depend very strongly on the profile gradient. And the key is really representing the turbulent flux as a sum of diffusive and convective pieces, and then using a Picard type of iteration scheme and not a Newton scheme. So there are no Jacobian calculations. And so again, I'm just going to pose this question to the audience because I'm very curious for other numerical methods for dealing with this kind of separation of timescale for transport to turbulence. Thank you for your attention. Questions?
It's very interesting. To answer your last question, I think it's quite interesting these parallel time methods. I don't know a lot about them.
Yeah, Ben Brown mentioned those to me earlier this week, so I'm also very interested in learning about them.
Steve, the parallel time stuff is that what you want.
Try and use the mic because it's for the recording.
Oh.
Yes.
Anybody else?
Just a vague suggestion, you might try changing one of the parameters in the problem, such as the mass of deuterium or something, to something that would make the timescales come together closer, so you could do an efficient solution. Then do it for several slightly different masses, and then try to extrapolate back toward the real mass using like a Pade approximation or something like that. It might, I've seen some of that, I've seen this somewhere, and I can't remember, but I've seen this trick done.
Okay, thanks.
Okay, our next speaker. Right there. So our next speaker is Han-Tao Chi from Princeton University, Successes and Lessons from Laboratory Experiments of Astrophysical Fluid Dynamics.
Thank you. The organizer for Dynamic came here. It's the very first time for me to speak geophysics, astrophysical course, geophysics, particle physics, fluid dynamics, everyone in the same room. It's very nice. So I changed the title a little bit because the success and lesson is kind of the same thing, depending on how to look at. So I want to give us my summary of doing past, actually it's 15 years, trying to do something astrophysical fluid dynamic experiment, which is not easy. So let me try to summarize in this outline way. So of course I can modify motivations by astrophysical problems, but the idea, the reality is so different. This is the one I want to emphasize in a way that two lessons, when the boundary is extremely important, which I didn't appreciate until I started doing experiments. Then we know geophysical fluid dynamics is more about boundary layers as well as fluid dynamics. And not as much as astrophysics. This is a different part. So it can be a really different way. It can be very harmful because their effects can be very confusing and it can sometimes mask the real result. But if once I understand it, sometimes you can use it for your advantage. It can be helpful, which is the first step when I'm going to talk about the near future. Can give you something that otherwise cannot be done. This is one lesson. The other lesson is for the unstratified Capillary flows are extremely stable. I'm going to quantify what I mean by extremely stable by all kinds of different ways trying to make it unstable. It's not easy. Okay, so the near future, well, we are really one step away because we know, well, hope we know, again, using the boundary for our advantage to detect so-called standard MI in the real world. Also, we are interested other astrophysical, like stratified case or geoplanetary applications, even solar fluid dynamics. That could be interesting next steps. Okay, so let me start with the astrophysical motivation, which is the accretion disk. And will be a subject of discussion tomorrow and day after tomorrow. So I want to be just quick. So there are three kinds of accretion disk. One is in the star formation disks, well, so-called a protostar system, which is a real picture about 2 years old. The other kind is the mass transfer between binary stars through accretion disk, which I don't find a picture, only a spectrum, not a picture. Maybe in the near future, sometime we can really take a picture of that. It'd be nice. The third one actually do have pictures. The center of a galaxy is very bright. Sometimes you have active galactic nuclei, which emits tremendous of the emission through the accretion process. Picture here, I was told, this is not the disk. This is a torus. Disk is really the pointer there. So it's not really resolved, but it gives you an environment that the disk is about. So there's so many different kind of disk, but there's a common key problem in terms of physics. So how to generate turbulence to effectively transport angular momentum required to explain observe the fast accretion through all the systems. Typically, there are follow the Keplerian rotation profile. So that question have generated lots of interest in past 20 or 30 years. John will talk about tomorrow, or maybe on Thursday, I guess. So I'm not going to steal his show. I'm sorry. But I want to talk my problem, motivated by his problem, which there's two major candidates in the unstratified accretion disk to generate turbulence. One is so-called MI, or magnetic rotational instability, which using Mach field, but in that case, it's a hot disk like the quasar or active galactic nuclei. Typically, the plasma are fully ionized, is very conducting, and it's easy to generate Mach field. It's hard to believe not to have Mach field. If we have Mach field, the idea by Barbara Hardy in 1991 is trying to destabilize otherwise stable flows by having a Mach field linking to, say, two objects together. You can transfer angular moment from one to the other to make one closer to the center, rotating faster, stretch the field line further, and make the one far away spin slower, therefore stretch further. This is a runaway process. Now, that has been demonstrated in 3D simulation. Again, I stole a little bit of John's show a little bit. I'm sure he will show you some more updated. I think it's like more than 10 years old movie I can show. This is not disputed. It has been recognized as one of the major, the major mechanism in the magnetized conducting disks. But for the disk as a code, it's not so obvious that MI will work because there's not sufficient ionization, such as the protoplanetary disk. Sometimes protostar disk is being used interchangeably, I guess. This is a real picture again. The idea there is, can you generate turbulence without Mach field? So the idea there is because we have a long history of the experience on terrestrial flows, whenever the Reynolds number is large enough, you don't worry about generating turbulence, always turbulent. And whether it's linear stability, it doesn't matter. So ideas from Reynolds himself, more than 100 years ago, he did experiments very carefully using ink to show whether ink can be diffused like this, like an onset instability like this. And he didn't know there's linear instability threshold at that time. But now we know they're all stable for pipe flows, despite the fact linear is stable, but always unstable as long as Reynolds number is large enough. And then we know supercritical transition to turbulence through the rough wall is relatively speaking, is a well-known phenomena in the fluid dynamics or engineering world. So now, for me, given in the near future, there's no hope to measure directly astronomical observation or through direct numerical simulation, either MI or nonlinear hydro in the real disk. So that's the value. We can try to do that in the experiment, whether you can test the idea, whether it can really working or not. So the basic idea is, actually, Jeremy Goodman, he's not here today, but he's my main collaborator. Back 15 years ago, we decided, well, we come together and say, well, let's try to do that experiment. So the idea is set up a concentric cylinder with different rotating speeds, have fluid confined between. Typically, we call it Iterate-averaging setup. In that way, so-called quasi-Keplerian means the omega-1 inner speed is faster than outer speed, but the angular momentum-wise is increasing function. The outer cylinder have more angular momentum than inner cylinder. We call it quasi-Keplerian. It's not power law dependent like a Keplerian flow. So we call it, that's why it's quasi. But in terms of regime-wise, it's the same. But we don't have gravity, so we have wall pressure to support centrifugal force instead. Then using liquid metal, which is conducting to test the MI with finite BZ, which you can calculate to destabilize the MI, or using water to study the nonlinear instability that we talk about. This is not new, actually. Just having turbulence in rotating flow is well known in Taylor-Quet or Quet-Taylor community. They have been doing since Quet, more than 100 years. Taylor, close to 100 years now. Actually, he did it 1923. So getting there. So there are very, very large number of history studying turbulence when inner cylinder is much faster than the outer cylinder. This is so-called radial line, the constant angular momentum line. So this is unstable for radial instability. I'm sorry, tailor instability. Sorry, tailor instability, not the radial instability. There's not convection. It's tailor instability. So there's lots of nonlinear dynamics, barification, turbulence, everything studied. On the other hand, this is solid body line. This regime is much less. And there are only a few work, but recently we have a work from Michael Buring. He started nonlinear transition to turbulence, so-called this regime. Question is in between, so quasi-coherent flow, in hydro, can we have like this nonlinearly induced instability, or in MHD can be linearly destabilized MRI? And the question I'm repeating again is, the first question is do nonlinear instability exist in such a flow? If so, how much they can transfer angular momentum? So this is, I want to do a summary for theory without using equation, just using names and years. It's not it's lots of work since Zaltowicz speculated back in the 80s, followed by quite a few people, speculation-wise. But first real numerical effort is Barbers, Honey, and Stone. They tried very hard, couldn't find it. They concluded with the range try, it's unlikely to have it. Then again, a few years later, no, that may be wrong. Maybe something wasn't done right. They speculated again, yes. I guess John come back again. We try to try it again, but again it's no, unfortunately. For some reason, early 2000s, suddenly there's a huge number of people. Actually, I tuned right into the, so I decided to stop. So many people speculate what kind of setup you can grow linearly. It's so-called not a non-modal mode growth, so that large enough magnitude could be unstable, then can have secondary instability, which feed back on the non-modal growth, then can sustain turbulence. It's very much like a pi flow idea, but nobody succeeded. It's all causing linear calculation or linear calculations. Then again, somebody else come in. They said already tried very hard, differently from John and Steve's group. They concluded no. And after that, died away, but never converged. Nobody say agree anything. Just let's say the status that is not converging. But same question can be asked experimentally. But here, it's lots of controversy, unfortunately, again. But I want to say, by today, it's converging, I think. It can be contested again. But let me try and go through quickly. So the first try is Richard, his thesis was done in France. He found some indication of the turbulence. He says yes. However, back in the silicon Colgate and used the global torque measurement, they say the torque measurement can be explained by Ekman circulation. So they say maybe not, even though no direct measurement. But we also, with our carburetor, Kageyama came to Princeton, with the spin down experiment, say the spin down time is about the Ekman time. So you don't need additional instability. So we say speculated no. And then with a new device I'm going to describe after that, we figured a way to break down the Ekman circulation to find a way to test this idea. We say it's no. But we had enjoyed about 5 years quiescence. Then as a Maryland group came back, say no, they found instability. It was surprising to us. So that motivated us to rebuild another experiment. We slightly improved the geometry and the control. And we repeated everything, but this time with active perturbation. And we couldn't find any. And then a Maryland group, together with the Netherlands group, which is a new group in Europe, joined the group. And they did together, they concluded last year, say the previous finding probably due to Ekman circulation. 4 minutes? Right? Okay. So maybe I just skip. This is a very good way to summarize. So last year, we did a scaling study and found, indeed, it's not there. So let me show you the most recent one. Oh, okay. I was surprised only 4 minutes. 12 more minutes, okay. Maybe I still skip because everyone knows Ekman. So I want to show you the, here's that. But that already, oh, I'm going backwards. So this is a new experiment back in 2014. This is an experiment we built after we heard this contradiction into the experiment data. So this new experiment had one ring, which is different from the previous one, the two ring, which is more complicated. But it's enough to break the global Ekman circulation to small Ekman circulation so that leave the most part is quiescent. And then we have also nozzles, 12 nozzles, 8 in the mid-plane for each side to perturb flow more actively so that they can really get turbulence going. So this is one of the try. We tried a few thousand combinations, all different power and the mode number. All of them failed, like this. Whenever we turn off the perturbation, it dies away quickly. As a matter of fact, it dies away transiently below the previous turbulence, no turbulence, noise level. As compared to, say, the Q equals 0, which is solid body actually turn off slower than Q equals 1.8 case. Q is like the rotational omega index of the R. So we concluded it's not there that easily, at least. And it's interesting, same year from Europe, there's a serious try, numerical way, to do almost the same thing. It's consistent with their decay of turbulence wherever it turn on the notation to the coefficient flow. So this is 2015, their conclusion about what happened in the mirroring experiment. The outflow of the angular momentum for the inner cylinder going actually radially through the Ekman circulation. And last year, we also did the Reynolds number scanning. So we scanned the Reynolds number by factor of 16. We see the quiescence stay there within the range we scanned. So at the moment, we're going to stop doing that because there's no point repeating the same over again unless there's a new idea or a new incentive for us. Yeah. So I want to move to the next question. Can we find a reason MRI in the real world? Because you can't just trust simulation everything or trust this observation everything because you don't resolve anything yet. So there, it's very difficult also. And some of them are due to boundary layer too. So that's a false alarm about more than 10 years ago. We know it's a circular layer instability. It's not really MRI. And there's a helical MRI version or the AMI version. Unfortunately, they are not really MRI. And they are not probably unlikely to be important for disks. And we found the circular layer instability all on, consistent with this one, and with comparison with simulations and such. And the reason we have circular layer instability is because the boundary effect. Let me jump to that. Actually, it's the next page. I want to show that, then move to. So if we impose Mann field through differential notating end caps, you can introduce the shear layer inside flow, which can be unstable. Let me see. Okay. So when it's imposed Mann field on top of this, we found the fluctuation shows up, becomes the M-1 mode. And we compared the linear theory and nonlinear simulation, found a very good agreement. We concluded this is hydro instability of a boundary-induced boundary layer, boundary-induced free layer in the flow, which is the unstable hydrodynamically, not MI, unfortunately. But we went to the regime predicted for MI. This is the speed and the Mann field. We did run into that, but I found it's very hard to find anything different. And why is that? We now realize, and the saturation level is so small to be detectable. It's only 2%. So we presented that in a meeting in Germany. A professor called Karl Lechner. He says, since boundary is so important, why don't you use that into the shear that is larger than you do viscous drive? So instead of using insulating boundary condition, can we use conducting boundary to inject more free energy for MI? Oh, that's a good idea. So Jeremy estimated about 1,000 times more effective inject free energy than the viscous boundary. And Wei Xin, he just presented yesterday some other topic. He used another code and verified that indeed the amplitude is much bigger if we're using a conducting boundary than the insulating boundary. With that idea, so we modified the device again. This is our original idea. We modified the design to one ring, but with a conducting copper about 2 centimeters thick each side, and in between is about 28 centimeter liquid metal. And this is new device, and it's a zoom-in version of the top part only. It's much more compact, easier to operate. So this is newest result, initial result. So we compared insulating case and conducting case. Everything else is the same. The one particular location, the main field increasing from 800 Gauss to 3,500 Gauss. And the flow changing in the insulating case is very slow and small. The insulating case, the conducting case, very immediate, very large. That showed importance, the conducting boundary. I would say it's very promising. If that's true, we can really detect MI in the near term. So I want to summarize. How many more minutes? 5 more minutes still? Oh, okay. I can go slowly, I guess. Oh, really? Okay. I can do slowly now, okay. So let me summarize. So in hydrodynamic case, we found this flow is extremely stable. We kicked it all kinds of different ways to make it unstable. It's not easy. So I would say no evidence that hydro non-linear instability will work for disk, from my point of view. Why? Actually, I don't really know, other than the argument that the coherent force can stabilizing. I guess that could be a very deep theory question. Why it's so stable? And it could be related to the hurricane stability, which is I found interesting from the literature. This is a paper published about 10 years ago, measured the hurricane profile, some airplane flying through. As I, which is a solid body, the speed goes up with radius, but after this I goes down in quasi-Capillary way. That's related or not? I don't know. That's maybe right crowd to ask. That could be related, could be wrong, yeah. So this is the second one. The third one is Ekman effect is very important, as we know. We have to use multiple rings to break down the global Ekman circulation, the local ones, that the global parts do required. For the MRI case, it's still very valuable, I would say, very important to search for the standard MRI. And we know the boundary condition is important, and that could, for example, the circular instability could have geophysical implications, because you can have tangential cylinder in the Earth, which be somewhat parallel to the main field, with differential notation between inner core and outer core, can generate a shear which can be unstable hydrodynamically. I don't know enough to say this case, but I want to ask, maybe you can tell me about this. Viscous dry is very inefficient, because liquid matter is very inviscid. So that's why MI is driven by that way. It's a very small amplitude. But with a conducting boundary, we are hopeful that get a large enough amplitude to be detectable. What's the feature? There's so many features inside. I mean, we have planned for gas dynamics, plasma case, stratifications. But today, I wanted to show 2 things. One is flow self-organization. This is actually Steve mentioned. Can you drive small-scale turbulence and drive it regulated by a large-scale flow, the zonal flow? This is the one is done by Mike Buring, who was previously a postdoc with our group, but now come back. The experiment is motivated by a so-called zonal flow on the surface of Jupiter, but also the tokamak, which is Jeff summarized nicely. So we had modified, remember the experiment, to have a beta plane. So sloped beta plane can be either way, positive or negative, with a perturbation jet in and out. Actually, I forgot which one. Maybe blue is in, the red, the yellow is out. The perturb flow, see if we can generate zonal flow. And it took a year before we realized the jet have asymmetry. In-jet, out-jet is not identical. Only if it's small enough flow rate is identical. If it's too much flow, you're going to induce symmetry that way. And we figured that way by Jordan Squire with Amitabh student now in the Caltech. They did the DSS calculation. confirmed the asymmetry of the jet in and out with too much flow. Now, with reduced flow, the asymmetry went away. We were able to reproduce actually Peter Reed's experiment done in the Bonobo, which, sorry, it's hard to see. With positive beta, go one general zonal flow, negative beta switch signs. This is a very nice check. It's really the beta plane approximation works in the rotating flow like this. This is one direction we want to go, trying to study flow self-organization. The other one, I'm talking with Mark, who is part of this organizing committee here, is about surface of the sun, which is also have to put a solar near surface shear near, which is a combination of rotation and a turbulence. He gave me the slides. I'm half understood. I don't understand fully yet. It's by it's different rotation. Actually, tomorrow he will talk about this. I don't have to repeat. The different rotation and the polar circulation are linked together in a way self-consistent. In between, there's the inhomogeneous turbulence from low and a large Rossby number in and out. So can we create a situation like this experiment to generate a shear net like this? This is very important because there's lots of implications in terms so-called convection conundrum about scale, which we talked about, we heard about yesterday. Solar cycle problems, and even there's an implication to solar observations. That's all I have. How many minutes do I have?
That's perfect.
Perfect. Okay. Thank you.
Very nice overview. I liked it a lot. So when you cited the work by Lesu and Longaretti on the possible theoretical outcome of the nonlinear instability, they said basically no as an answer, that it would not drive it. But if you look more in detail in the paper, then they do not argue that it would not work, but they say that if it works, it might be very unimportant, because they say that, or they speculate, extrapolate, that the resulting alpha Shakura-Zonyar viscosity would be inversely proportional to the critical Reynolds number. So that if you have a Reynolds number of, I don't know, 10 to 4, 10 to minus, 10 to 4, 10 to 5, the alpha value would also be extremely low.
Yeah. So
my question is, so I talked about this with Jean-Paul Zahn, and he said no, one cannot do such an extrapolation. So once things are getting nonlinear, you have no idea what will happen. So what is your opinion about that?
Actually, in the paper we published in 2006, we also speculated that larger the critical Reynolds number for nonlinear acquisition is less important for the transport point of view. So in the argument 2005, this when the Longaretti made the same argument. We use that because we went to 2 times 10 to 6, the new signs in nonlinear transition. If anything above that, you can calculate what is the alpha beta. Actually, I had the slides, I had to skip and show it's very unlikely, unless some other mechanism, maybe crazy idea. But regular nonlinear instability is because it's more efficient to transport angular momentum through nonlinear way rather than laminar way. Therefore, there's a tendency for flow to make transition to that state. If that's a regular argument, then this is still, I think it's still solid. Larger the critical Reynolds number for transition is less important. Do you agree? Because you have to compare with molecular viscosity. Right, so this is the kind of common sense kind of argument. And I don't think they had an even more rigorous argument than this is common sense. But I want to know from you, maybe other people, stratified case, you put in field, you have new ideas, and I have no idea how that works. But so far, I'm doing non-stratified, so it's called incompressible. For the stratified case, like your case, could be another way. So I want to hear, the rest of your talk about this.
Any other questions? Okay. Questions?
Just going to ask about the stratified case. If there's a way to cleverly create such a structure by composition gradient or something.
Actually, experimentally, we started the way to make a more stratified. there are certain salt you can use.
Yeah, to take a composition.
Yeah, you can build an experiment with stratification enough. Maybe how much is enough is a question. But the problem is you couple with notation, right? So it's not a convection case. If too much notation, you stratify radially, inversely actually, not vertically anymore. So you're starting a different problem. So it had to be just about right notation, but not too much. So we'll see. Yeah, maybe there's all kind of different salt. Certain salt, it can be if you do right, you can do little slowly, very heavy bottom, very light here. You can have one scale height, a few scale height. That'd be nice. Yeah, yeah. That'd be ideal. Yeah. I haven't get a chance to talk about this because I want to hear the theory idea first before I do experiment. Experiment is like a 15 years effort. If one decides, you can easily change. Yeah.
Okay, our next speaker, Peter Davidson, and he's going to tell us about scaling laws for planetary dynamos driven by helical waves.
Oh, already there. Okay, good. Sorry.
Is it still on? What is on? It is.
Okay, so thank you very much to the organizers, and it's been a very nice meeting so far, I think. I'm very conscious of the fact that it's been a long day and I'm the last thing between you and getting out of here, so I'll try and keep to time. And just to keep you awake, I'll occasionally throw in a few things which I think are slightly controversial. I more or less believe everything I'm going to say, nonetheless. So what I want to talk about mostly is, or get to eventually, is this idea that there's scaling laws of planetary dynamos. By that I mean, if you know something like the heat flux through a planet, how fast it rotates, the size of the core, can you predict the magnitude of the dipole moment or the intensity of the convection within the planet? There's a number of people are looking at these sort of scaling laws now, driven mostly by the results of numerical simulations. But when I get to scaling laws, I want to distinguish quite clearly between the numerical dynamos and the real planetary dynamos, because I think they scale quite differently. But before getting to that, I want to give you a bit of background about planetary dynamos for those of you who aren't really dynamo people. So, of course, the name of the game, let's see if this stick works, is you have some convection in the core of a planet here, and it stretches out and twists the magnetic field lines. Of course, that intensifies the field, keeps the energy of the field high. But the real question is not so much can you intensify the magnetic field, but how do you create a rather stable long-term magnetic field, which is a dipole pointing north-south aligned with the rotation axis? What sort of convective motions will give you this sort of long-time, steady, relatively steady planetary dynamo? And up until about 1995, so think of Gary patented this picture, you're a rich person by now. Up to about 1995, I think most theoreticians thought this encapsulated what was happening, the so-called alpha omega dynamo. There was two steps to the sort of theory. The idea is that if you start off with a north-south dipole, it's a natural consequence of angular momentum conservation in a rotating body that you should get some differential rotation. And you've got differential rotation that's going to shear out the north-south dipole, give some east-west field. And then you have to convert that east-west field back into a north-south field to complete the loop. And that was thought to be done by Parker's offer effect, or lift and twist mechanism. And for those of you who are not dynamo people, it works something like this. You imagine that in the core of the planet, there's lots of helical convection cells. And as these convection cells punch through the east-west field, so this field here, they lift and twist the field lines, raking off flux loops, and that induces a current, or an EMF really. And that EMF, it turns out, is parallel or anti-parallel to the background field. If the helicity is positive, so that the streamline's got a right-handed twist, then you get current which is anti-parallel to the background field. And if the helicity is negative, so it's a left-handed spiral, you get current which is in the opposite direction, parallel to the background magnetic field. This asymmetry in the, depending on the helicity, turns out to be very important for these sort of dynamos. So this is a picture up to about 1995, I would say, and then one of the first, I think, the first serious dynamo simulation. Since then, what's happened, I think, in most of the simulations is this east-west field has got smaller and smaller and smaller. And now most of the simulations, numerical simulations, have an east-west field that's not much larger than the north-south field. There's very little evidence of a significant omega effect. And most people now working in these sort of numerical simulations tend to think of the simulations as being so-called alpha squared dynamos. That's to say, as before, you generate the north-south field from the east-west field through the alpha effect. But the generation of the east-west field is also produced by an alpha effect. So it's an alpha effect twice. That's essentially where we've got to. But the key thing is, when you follow the steps in either an alpha omega or an alpha squared dynamo, what turns out to be absolutely crucial is that the helicity has to be of opposite sign north and south of the equator. One sign in the north, another sign in the south. A natural question to ask, and to me it's the leading order question in planetary dynamo theory, is why is it that the dynamics in the core of a planet are such that you always get one helicity of one sign in the north and helicity in the other sign in the south? What is it that's segregating the helicity? And that's really one of the issues I want to tackle before getting to the scaling laws. So why should the flow in the core be like this, asymmetric about the equatorial? I mean, certainly true in the simulations you do see this. This is a typical result. The dynamo tends to reside outside the tangent cylinder here. This is azimuthally averaged helicity. And in this case, so blue is negative, red is positive. In this case, you get negative helicity in the north, positive helicity in the south. And that's very typical. Nearly all the simulations look rather like this. I should say that doing azimuthal averaging hides a multitude of sins. If you take a slice, a vertical slice, the picture is altogether much more complicated. Here's the azimuthal average for the helicity in this simulation. But if I take a slice, you can see it's much, much more complicated. There's a lot more going on. In some sense, we're necessarily talking about statistics. Okay, so most of what we know, or think we know, about planetary dynamos comes from these simulations. There have been heroic efforts, I think, and they're extremely interesting. I guess about 1995, there's a good euphoria about the simulations, and then people began to realize that there were some problems with them, and so now there's a bit of argument going back and forth about what's really happening in the simulations as opposed to planet. And the point's already been made. The thing that's remarkable about the simulations, I think, is that they capture many features of planetary dynamos. You get this north-south dipole, aligned with the rotation axis. It's relatively stable, but reverses occasionally. You can either capture things like westward drift and so on in the simulations. So in some sense, they're quite remarkable. On the other hand, they're absolutely nowhere near the right parameter regime for a planet. There's many, many things which is away from planetary values, but probably the most important two are they're extremely viscous. If you use the Ekman number as a measure of viscosity, they're overly viscous by a factor of about 10 to the 9. So liquid metals have a kinematic viscosity somewhat less than the air in this room. When you do something which has got a viscosity of 10 to the 9 larger, essentially you're simulating in your numerical dynamo something with a viscosity of something like semi-set concrete. So these are really, really viscous simulations. That's important to remember. That'll come back into the talk. So they're massively viscous. That's one point. The second point is that they're typically very underpowered. So what do I mean by that? So a lot of the simulations about 10, 15 years ago would have been about 10 times critical. So the heat flux is about 10 times that, which would first kick off convection. And the sort of flow pattern you get at 10 times critical is this. The flow pattern is these cyclones, anticyclones arranged around the inner core, packed full of helicity, generating the dynamo. That's where the dynamo resides. That's the flow pattern. If you crank up heat flux, or the driving force for convection, to about 50 times critical. In some sense, the basic building blocks don't change. You get these sort of characteristic cyclone-anticyclone pairs aligned with the rotation axis sitting around the inner core, but they're starting to become much more dynamic. Here, these objects are rather static, slightly boring, rather laminar. These are much more dynamic. They're waving around like grass in the wind. progressively much thinner, and it's no longer clear that these objects are connecting with the mantle top and bottom. They're becoming increasingly interior objects, perhaps. So, underpowered. So this is about 50 times critical Rayleigh number. In the real planet, or on the Earth anyway, you're probably something like 10 to the 4 or 10 to the 5 times critical. Much, 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 much more strongly forced. So if this trend is to be believed, in a real planet, you've got something that's really very chaotic, fine-scale structure, possibly the same sort of kind of structure, columnar vortices, cyclone, anticyclones pairing off, but this kind of static image is sort of lost. Okay, but nonetheless, even though we're a long, long way from, or those doing the simulations, they're a long, long way from real planetary cores, they do capture a lot of what's going on, or appear to. So for me, the really interesting question is, you know that the simulations are getting a lot that's wrong, but they're also clearly getting something that's right. And the key question is, what is it that they're getting that's right, I think? Okay, so I said earlier, the key point, if you want a dynamo, is that the helicity must be one sign in the north, another sign in the south. So let's ask, why should that be? And I think people were sort of really very influenced in the early days by this kind of quasi-static image where you get these massive, great, lazy, columnar, Taylor-Proudman type columns that just sit there doing very little except grind away in the mantle. And so a cartoon sort of emerged that, well, maybe the helicity is driven by Ekman pumping, these things just sitting there grinding on the mantle. And I think there was a little bit of a hint of that yesterday. And indeed, that works. If you think about the Ekman pumping that comes from either the cyclones or the anticyclones, it's always going to give you negative helicity in the north, positive in the south, exactly as you see in the simulation. So that's consistent with what's observed. But as early as, I think, about 1999, there's a very nice paper by Gary, Peter Olson, Willie Christensen, who observed that if you increase the driving, you go from, say, 10 times critical to 50 times critical. And remember, planets are about 10 to 5 times critical. The generation of helicity starts to move away from the boundaries. It's no longer Ekman pumping. It appears to be more in the interior of the planet. So it seems to me rather unlikely that this explanation is really happening in a real planet. I don't think it's Ekman pumping. So what I'm really suggesting is that viscous stresses are, in some sense, entirely irrelevant for planetary cores and for generating helicity. There's a number of reasons for believing that. One is simply that the viscosity is so small. The Ekman number is 10 to the minus 15. It's hard to believe you can generate viscous stresses of a magnitude that's sufficient to control the whole structure of the flow pattern and generate the magnetic field. You have to get down to length scales about this size to generate significant viscous stresses, and the ohmic dissipation won't let you do that. There's several other reasons. One is, one of the things that's very striking is that if you look at the planets, Mercury, Earth, Jupiter, Saturn, the magnetic fields are all very similar. They're all dipolar. The dipole is more or less in line with the rotation axis. And even more striking, the magnitude, the intensity of the dipole is suitably normalized, looks rather similar in all cases. So here's BZ, the average axial magnetic field in the core. You can get that from the observed dipole moment. Convert it to an alpha velocity to make it dimensionless. You divide by rotation rate and planetary core size, that's R sub C. And what you get for Mercury, 5 times 10 to the minus 6, the Earth 13 times 10 to the minus 6, Jupiter 5 times 10 to the minus 6, Saturn 2 times 10 to the minus 6, and for Willie's benefit, I threw in a low mass star at the end here. The remarkable thing is these numbers look very, very similar. So all these planets, which have very different rotation rates, sizes, internal constitutions, materials, they're all producing dipoles that look rather similar. So one might rather suspect that in some zero-order sense, the dipole mechanism and the helicity generation would be the same. Then where's the mantle in Jupiter and Saturn for the Ekman pumping? Nowhere for these columnar structures to grind away producing the Ekman pumping. So that's another reason for thinking that Ekman pumping is not important. Another is this, what I've mentioned already, that as you increase the driving, these structures increasingly, I think, become interior structures. They're not abutting on the mantle. And the final one is that if you run these simulations with a slip boundary condition, free slip on the surface, again you get a dynamo, and they're not so different from the dynamos you get with no slip. So I would suggest that Ekman-Hartmann can't really drive a dynamo on a planet. It probably contributes to some of the numerical dynamos there. If that's true, then we're obliged, I think, to find a mechanism for producing and then spatially segregating helicity in the planetary core of one side in the north, of another side in the south. That segregation of helicity north and south of the equator, which I think is interesting. And that mechanism should be independent of viscosity. I think internally driven, you think about the gas giants, and it ought to be physically very simple and very robust, because it appears to work fairly well across a wide range of objects. So let me offer you a candidate. I'm not saying this is what really happens. A possibility, which we can argue about, perhaps. And a clue comes in the fact that if you look at these simulations, what you tend to find is that outside the tangent cylinder, and in these simulations, the alpha squared dynamo tends to reside outside the tangent cylinder. The equatorial plane is very strongly agitated. So here's an example taken from Zechariah and Roberts, which is a rather extreme example. Here we're looking at the radial velocity azimuthally averaged in the core. And what you see is something that looks like a very strong radial jet. So very strong velocity coming outward. Strong actually is again, this azimuthal average is a little bit misleading, and I take an equatorial slice through this. I see that this is not really a jet at all. In fact, what you've got are these things here. You've got lots of plumes emanating from the inner core, floating out towards the mantle, taking about 300 years to get to cross the annulus. But anyway, we've got this concentration of flow out in the equatorial regions. That's going to carry the heat with it to some extent. And in this simulation, this is the temperature distribution. And again, you see it's relatively hot in the equatorial regions, cooler here, north and south. So what I have then is a rapidly rotating body. And I have some agitation in the equatorial plane. I've got a rapidly rotating body which is being agitated. That agitation is, in some sense, obliged to produce waves. Those waves could be inertial waves, or they could be magnetostrophic waves. The point is that both are helical. Inertial waves are helical. Magnetostrophic waves are helical. And they share in common the fact that upward propagating waves always carry negative helicity, and downward propagating waves invariably carry positive helicity. So all the waves which are generated by the agitation in the equatorial regions propagating up will carry with them negative helicity, exactly the helicity that's seen in simulations. And all the waves propagating downward will carry with them positive helicity. So we have a natural mechanism both for generating helicity and for spatially segregating that helicity exactly as required by Multiscale. So that's essentially my hypothesis. I'm very willing to listen to alternative ideas. Skip this. So I could talk about either inertial waves or magnetostrophic waves. Magnetostrophic waves are perhaps a more likely case, given the relatively strong magnetic field in the core, but the inertial waves are slightly easier to talk about, and I think most of you are more familiar with inertial waves. It doesn't matter which class of wave I choose to talk about, the story is rather similar. So I'll focus on inertial waves. And inertial waves have a rather remarkable property, which is that if I take some localized disturbance, so buoyant anomaly floating out along the equatorial plane towards the mantle, and it radiates energy, then although I get a wide spectrum of waves coming off that buoyant anomaly, depending on the frequency, they can go every way. Inertial waves have this very special property of self-focusing of the radiation. Say that although I've got radiation going in every direction from this, actually someone showed this picture earlier. It was Fabian. So if you've got a buoyant anomaly here, radiating waves in which direction, what you find is that most of the energy actually spontaneously propagates along the rotation axis. Automatic self-focusing of the radiation. And the reason is the dispersion relationship and the group velocity. The group velocity is at right angles to k. So here's my disturbance. All my k vectors, which sit in the horizontal plane, all flip up and propagate energy along the rotation axis. So I'm going from a plane in k space, all the energy in a plane in k space, to a line in physical space, and that automatically focuses the energy onto rotation. Very robust result. Doesn't matter what sort of disturbance I put in here. And you can see that in this toy simulation here. Some disturbance at t equals 0 in a rapidly rotating fluid. Just let it go. I get radiation, some off-axis radiation, but most of it's going up as a wave packet upward. And some of it's got, of course, got energy going downward. And I suspect this is why you see these columnar structures in many of these simulations. Okay, so here's just to fill in the gaps. So I asserted that the upward propagating waves carry negative velocity, the downward propagating waves positive velocity, and this just illustrates the point. So in this, again, this toy simulation, periodic Q, background rotation, omega, I put some disturbances in the plane layer. These disturbances happen to be just little vortical eddies, but it could be almost anything I want. Anything that disturbs the fluid. That's the initial condition, and then I let it go. In this case, the velocity number is about 0.1. And I look at what I see at time omega t was about 8. And what I see is this mess here has organized itself very quickly. Lots of columnar wave packets are propagating downward and upward, and they're colored by helicity. Red is negative, green is blue. And what you see is this front of negative helicity coming off, what I might call now the equatorial plane, and this front of positive helicity propagating downward. I'm also seeing at the same time some structuring of the turbulence. So initially it's just a mass, it's now organizing itself into columnar structures. And in the turbulence community, people normally attribute that to resonant triad interactions. There's not a single resonant triad to be seen here, of course. Time scale is too short. It's all linear. You get the structuring, that's just really an aside, this natural structuring through linear dynamics. But the key thing is I generated and then spatially segregated the exact phase I need for an alpha squared dynamo. I really better speed up to get them. Okay, so you can push this a bit farther. You can say if I isolate a buoyant blob that's floating out along the equatorial plane, here it is. What's the characteristic dispersion pattern I get in the form of inertial waves? And what I find is I get 4 wave packets, an anticyclone here, an anticyclone here, a cyclone here, and a cyclone here, negative velocity up here, here. So I get fluid spiraling downward here towards the equatorial plane, spiraling back up. I get fluid spiraling up here towards the equatorial plane and spiraling back down. And that's very typical of the sort of flow patterns you see in these columnar structures in the simulations. There we go. So here's an example of that numerical simulation. We've got some buoyant anomalies spread along, again, what I'll call the equatorial plane. And they're drifting slowly in the y direction of gravity, but they're going so slow you can't see the movement. And here are the structures, the wave packets coming off them. This is colored by axial velocity. So that's showing that these are growing off as cyclone-anticyclone pairs. This is colored by helicity. So again, you see the negative helicity going up. Positive. That's the generic flow pattern I get from buoyant anomalies in the equatorial plane. This is a typical dynamo simulation, and the structures don't look so dissimilar. So the basic hypothesis is that this agitation in the equatorial plane is providing both the helicity and the segregation and allowing the dynamo to operate. Changes a bit if you put a magnetic field in, but essentially the same mechanisms work. Finally, to the scaling laws. Okay, so if you buy into all of this, you've got these wave packets continually coming from the equatorial regions towards the mantle, you can then construct a sort of partly predictive set of scaling laws. The input is, so you've got some kinematics up here, MHD kinematics. The input to this is that the EMF is driven by the alpha effect in the usual way, That EMF has to be sufficient to support the large-scale magnetic field by Ampere's law. Introduce dynamics in two parts. You demand that the curl of the buoyancy force is of the same order as the curl of the Coriolis force. It's crucial to take the curl first. You don't equate buoyancy to Coriolis because in this sort of quasi-geostrophic structures, of course, most of the Coriolis is balanced by pressure gradient. So you take curl first. That's why Alcessa number equals 1 doesn't work. And then the final thing you do is you do an energy balance. As these wave packets propagate up, they generate EMF and field. But they also produce dissipation. If you're statistically steady, that dissipation must be balanced by the rate of working of the buoyancy force. Balance that you threw into boot. So these are the three sort of inputs into the theory. You do about 20 pages of maths. What you get at is the following. One of the key parameters is the rate of working of the buoyancy force per unit mass, P bar, which you can equate to the heat flux out through the core, and that's something that people hear about for the Earth, for the gas giants. And from this P bar, you can introduce a velocity scale, which is characteristic of the forcing. I've called it V sub P, which is P bar times the core size, to the power of 1/3. And the sort of things you'd like to predict, knowing this, is what's the characteristic intensity of the convection, that's measured by, say, a Rossby number, and what the characteristic dipole field strength is, perhaps measured by some characteristic Alfvén velocity. And the other key parameter that enters into this is the transverse dimension of these objects, these interior objects, these thin columnar structures. So all the mass in this lot here, and eventually what pops out of this is just nothing more than this simple expression here, that the cube of my characteristic velocity, my forcing velocity V sub P, scales as the Alfvén velocity squared times lambda is the magnetic diffusivity in the core. Delta is my transverse dimension, which I don't know. Here's omega, background rotation rate, delta, and u squared. And then we immediately hit a problem. We don't know what delta is. We don't know what the small scale is. Except we do for one class of dynamos, but only one class, and that's the numerical dynamos. We know what delta is in numerical dynamos because they're massively, massively viscous. Remember, it's something like semi-set concrete simulating on the computer. So massively viscous that delta is just set by this viscous balance that we saw earlier today, that delta is just Ekman to the third. So for the numerical dynamos, but not the planets, delta. So we can take this, put it into here, and see if our scaling laws at least are consistent with what the numerical simulations get, and the answer is yes. So you add that estimate of delta to the state only, never true for planet, but true in the simulations, to these scalings. Here, so this is the Rossby number scaling. So this is a measure of the intensity of the convection, and it's predicted to scale as pi sub p is essentially my forcing. Here, Ekman number to minus 60, minus 6. So the red line is the predicted scaling. These are a suite of numerical dynamos. It seems to pick up rather well the scaling for the Rossby number. You can also predict the dipole field strength as measured by the RMS field, normalized by omega r. I've called that pi sub b. Here's pi sub b, and it's predicted to scales up here. That's the prediction. These are numerical dynamos. So it seems to compact quite well the data from the numerical dynamos.
These are numerical dynamos of concrete.
Yes. So not planets, exactly, and that's the point. And here's to reinforce that point. You can then ask, so what's observed in numerical dynamos is if you force a little bit too much, more than your computer would like, you lose the dipole structure. You also lose the columnar structures. Still get, in some sense, what plasma physicists might call dynamo. You get lots of magnetic field stretching, so you generate magnetic energy, but no dipolar magnetic field. That, I suggest, is because that when you get to a small-scale Rossby number of order 1, the fluid is no longer able to sustain inertial waves. And the fluid cannot sustain inertial waves, it can't sustain a quasi-geostrophic flow, and it can't sustain helicity generation and segregation. So the suggestion is that when the small-scale Rossby number gets to 1, you should lose the dipole. And so we can go back to our scalings for the planets, for the numerical dynamos, but not the planets. And we can ask, when does my small-scale Rossby number with this scaling for delta go to 1? And the prediction of the scaling is that that happens when, sorry, I've changed the notation, REQ is a really number based on the heat flux, but that's just my pi so here. REQ is a normal notation in this community. That should happen when REQ over Ekman is equal to 1. So I plotted REQ divided by Ekman along this axis. F dip is a measure of how dipolar your magnetic field is. If F dip is bigger than 0.5, it's usually classified as a dipole. If it's less than about 0.3, it's usually classified as non-dipolar. And what you see is this does a pretty good job of sorting out the dipolar fields from the non-dipolar fields. So again, the scaling laws can predict when you lose the dipole. You just get magnetic field stretching, but no organization for large-scale field. Going back to your point about the concrete, this is the prediction from the scaling laws if I use this viscous scaling for delta, which I suggest cannot happen in a real planet. So let's test that. Let's put the Earth on this plot, and it sits way over here, and it should be non-dipolar. Of course, it's a dipole. The reason, of course, is that delta is not being set by viscous stresses in the core of the planet. Okay, 1 minute. I'm almost there. Okay, so what about real planets? So we don't know what sets delta in a real planet, in a planet. And in fact, it's probable, I think, that it's different for, say, the gas giants, terrestrial planets, and so on. There's no reason to suppose it's the same, unless it's tempting to try and get some universal scaling. There are a few things you could try. You could say, well, was it set by the fact that the Alsace number is order 1? That's a very common rule that people working in planetary dynamo theory use. I think it's completely wrong. And it doesn't work. If you use that estimate for delta, what you find is that the gas giants would all be multipolar, not dipolar. That's not right. You can try Willie Christensen's suggestion that the magnetic field strength is independent of rotation rate. That doesn't work for the same reason. The only simple way of getting something that's self-consistent I found is that if you assume that the growing magnetic field from some transient growth saturates at the lowest magnetic field strength compatible with a given heat flux, that does allow you to estimate delta. The reason why it should do that, but it's worth trying. And when you do that, you find the following predictions. You find that dipole field strength dressed up as an alpha in velocity scales in this way. These are the predicted values from the scaling, 10 to the minus 5, 8 times 10 to the minus 5, 15 times 10 to the minus 5, 11 times 10 to the minus 5. And these are the measured values here. And this kind of significant difference, but at least they're all 10 to the minus 5. And that's about as good as you'd expect, because you don't know things like the magnetic diffusivity to within a factor of 3 or 10, and it varies from decade to decade. And there's some uncertainties in the heat flux, although Peter's the expert. Anyway, it seems to be not too bad. Okay, so in conclusion, the big messages are, 1, viscosity, I think, is completely irrelevant for a planetary core. Maybe that's obvious once said. It keeps coming up again and again in meetings like this. 2, if that's true, we are on our bound as scientists to find a natural mechanism which is very robust and interior to the planet, which generates and then segregates helicity. I've offered you one mechanism. That may not be the thing that really happens, but at least it's a trial object you can think about, which is that the helicity is carried off the agitated regions near the equator in the form of helical waves. And the third point is that if you bind that, you can get scaling laws, and they seem to work both the numerical dynamos, if you demand semi-set concrete in the core, and are not inconsistent with the observations for real planets. Overrun, sorry.
Thank you, Peter. Any questions? Mark?
So in Jupiter and Saturn, you have a density stratification that gives you a helicity and a variation in the north and south. In Jupiter and Saturn.
Maybe. I still go back to the fact that, as far as one can observe, the properties of these dynamos all look remarkably similar across a wide range of objects. So Occam's razor, to me, yes, the first thing to do is to look for a common source of dynamo action in all the objects. If you've got, the great thing about having lots of planets is if you've got a pet theory for one planet, the first thing you should do is try it against the other planets.
Well, anything with a density stratification is going to generate opposite signs of in so stars, gas giant planets. The core of the Earth might be a little different because there's not much density stratification.
So this goes back to Raymond Hyde, and it's discussed in Keith Moffat's book. I don't like it very much because it's, so you've got to do things. You have to be an efficient generator of helicity, and you have to also segregate it. You get the segregation from the fact that G or omega is anti-symmetric about the equator, but I don't think it's an efficient helicity generator. Generates the weak components of helicity, not the dominant components of helicity. So I don't disagree that it's a possibility, but again, just based on the evidence, I don't think it's a strong contender. Well, I did put a star in earlier for your benefit. What's remarkable is that low-mass M dwarf actually sat with exactly the same, more or less, dipole field strength as the other. I don't know about stars. Think about the planets are all rapid rotators. Stars, less so, and it's not so. This all hinges crucially on the fact it's a low Rossby number. So I'm really, the M dwarf is just a tease.
Peter, you sort of dismissed viscosity. You said the Ekman layer is so thin you couldn't really see how it would affect the whole bulk. Of course, that's the concept of a boundary layer, but we can discuss that in some detail. But the whole argument is predicated on surfaces being smooth, and you have a viscous flow around a smooth object and things like that, but that can't be true. So in fact, you have an effective Ekman layer, which depends not on physical viscosity, but on some kind of eddy diffusivity. Okay, so it must be, that must be the case, right? I mean, you can't have smooth surfaces with viscosity of 0.01 or whatever.
So this would be the standard sort of atmospheric or oceanic response, I think. That's true. So Ekman layers in the ocean, but still small viscosity. So there's two answers to that. The first one is that in a system where U dot grad U is almost completely negligible, I'm not quite sure where the Reynolds stress comes from. That's to say, I'm not sure what it means to talk about an eddy viscosity. How do I get momentum transfer when U dot grad U is small?
I can imagine having a rough surface and creating a whole lot of vorticity near the surface, even though the viscosity is small. I mean, it's entirely possible.
So that again has been looked at extensively. Again, it's Raymond Hyde, in fact. Going back, looking at the bumpy mantle essentially, and what you get are these wave packets coming off the bumps. But it's rather similar. To me, it's not a very efficient mechanism for helicity generation. The wave packets coming off actually tend to use helicity of the wrong sign, because the waves are now coming from the mantle towards the equatorial regions rather than vice versa. So it's coming down with positive, up with negative. And in the simulations, you see the opposite.
There is no efficiency in any of these processes as far as I know. Efficiency could not be an argument that one could use.
Well,
I'm not disputing your arguments.
I would say by efficiency, I mean something that's robust, not very sensitive to some particular geometry. But then even if you want to put in something like an eddy viscosity, which I have problems with, you still have to counter all the other arguments. Plus leaves in 1 minute, you know.
Okay, sorry. The question is, you say if L number equal 1, that means your L number.
L number, yeah.
Equal 1, it means your Coulomb force is about the same the Lorentz force.
Which it shouldn't.
different, but your inertial wave is ignoring the Lorentz force. If you add it back, your initial wave will be modified significantly by its Lorentz force.
In fact,
so
so
like
I agree. So I gave you the kind of low magnetic field picture because it's easier to tell. So if you then embrace the fact that these inertial waves are punching through a magnetic field, they probably, not necessarily, but they possibly convert into magnetostrophic waves, which then become essentially very anisotropic structures. But in some sense, the story doesn't change because they also carry negative velocity upward, positive velocity downward. The main horizontal. Vertical doesn't do very much because it's competing against a very strong, so Coriolis is very strong, rotation is very strong. It's a very stiff spring. So a weak vertical field does nothing to the waves.
I have a quick question. Just you said it's
regarding
the forcing. So since you have huge viscosities and you want to have supercritical Rayleigh numbers, don't you need to overforce it really strongly to get a supercritical Rayleigh number? I don't understand why you say it's underforced.
So there aren't, well,
in terms of like watt per meter squared. Like
so you're talking about the limitations of the simulations, and I guess the point is you can't get to very low Ekman numbers, and so therefore you can't force very high. Force too high, then it multipolar.
Yeah, but in actual watts per meter squared, you're putting in orders of magnitude more than what you have on these planets, aren't you?
Not so much for the Earth, but I think you're looking at different things. You're talking about how much power you're putting in. How much? What is the luminosity in the geodynamos, the numerical geodynamos, and it's in a reasonable range. But even so, the viscous work being done is like you say, orders of magnitude larger than it should be.
Many, many orders.
So when you say it's only slightly supercritical, it's the critical Rayleigh number is very different for these two problems.
So R sub C is very different for the numerical on the planets. That's the point.
Yeah.
But nonetheless, I think what's relevant to me anyway is where you are relative to R sub C.
But it's not where you are relative to, if you think about Jupiter, how much heating you have from the interior, then you're imposing a much stronger heating than that there actually is there.
Well, the bus is there, right?
Doesn't matter. You're still.
Batteries will leave it. Oh, yes, 5:40. We have to. The shuttle bus is out there apparently, and it's ready to leave. Let's thank everybody.